Hello and welcome to For Math's Sake. Today we have an interesting problem that is an application of stars and bars. It reads as follows: how many 5-digit positive integers exist where the digits are non-increasing from left to right? An example is given. 87743 is a number that fulfills the condition, but 78987 does not. For reference, we're just going to call these numbers falling numbers. Now you could just look at all of the 5-digit positive integers and see which ones are falling numbers, but that would involve searching through 90,000 numbers, which could take 50 hours, right? So how about we try to come up with a more intelligent and efficient solution? Let's try to generate these numbers. Here we have A, B, C, D, E representing the digits of a falling number. Now, A can get whatever value we want it to take, except for 0. B has to be smaller or equal to A. C has to be smaller or equal to B. D has to be smaller or equal to C. And E has to be smaller or equal to D. Now, using a tree of decisions, let's try to generate a falling number. Let's say A equals 2. Since that is the value of A, B has to be smaller or equal to 2. Let's say B equals 1. C has to be smaller or equal to 1. Let's say C again equals 1. Now, let's say D equals 0. Automatically, that means that E becomes 0. Why? Because there is no other digit other than 0 that is smaller or equal to 0. So when we have a 0 in our falling number, all of the digits after it have to be 0. Now this is a way to visualize falling numbers and to generate all of them. But how many do we have to generate? We'll cheat a little bit and use code in order to look at all of the 5-digit positive integers and see which ones are falling numbers. 2001. That's a lot of numbers to generate, much less than 90,000, but it's still very slow and inefficient. And what if you had to look at 7-digit positive integers, 1,000,000-digit positive integers? It's not really in the spirit of problem solving. But let's keep this idea of generating falling numbers. Let's just improve it. And here we have stars and bars. We have our set of digits 987654321, right? And we have a little pointer that initially starts at the value of 9 but moves along this set of digits. We're going to try to write a falling number as a sequence of stars and bars. Whenever we come across a star, we type out the value of P. Whenever we come across a bar, the value of B becomes one less than itself. So, for example, we have this sequence right here. Let's translate it. We have 1 star, P equals 9, so 9. We have 2 bars indicating that we'll subtract 2 from P, so P becomes 7. We have 2 stars, so that means that we'll type 7, 7. Then we have 5 bars indicating that we'll subtract from the current value of P 5. So P becomes 2. We have 2 bars. We have 2 stars, so we'll type out 2 twice. And then we'll just type out the remaining 2 bars so that the final value of P is 0. And so we have a P that traverses the entire set of digits and helps us express, in this case, 97722 as a sequence of stars and bars. Now, we reduce this problem to in how many ways can we arrange stars and bars in order to get a falling number, because all falling numbers can be written as a sequence of stars and bars. We have 5 stars, digits in the number, and 9 bars, the amount of times we increment, the amount of steps our pointer friend takes. We have 5 plus 9, 14 positions. And here's the thing. If we have determined all of the positions for the stars, then automatically the positions that don't have stars become positions that have bars. So essentially, in how many ways do we have basically empty boxes? In how many ways can we put 5 items in 14 empty boxes, right? Each box having no more than 1 item. Now, it'll probably look very similar to 14 choose 5, but let's explain that number. So in how many ways can we place 1? There are 14 available spots, so 14. Let's say we place it here. In how many places can we place 2? Since 1 room is occupied by 1, it'll have to be 13, the remainder that are left. There are only 12 rooms left, so 12 options for 3, 11 rooms left, 11 options for 4, and 10 rooms left for 5. But here's the thing. This algorithm is counting sets that shouldn't really be counted more than once, right? So for example, it considers these 2 sets that, notice, the values of zeros remain where they are, but the digits over that are greater than 0 are just switched around. So for example, 4 switches with 5, 1 switches with 2. Here's the thing, it counts these as being different, but in our case, there's no difference between the first star and the 4th star. And so we want to get rid of all of these extra sets that we're counting. How do we do this? Well, how many positions are there available for 1? 5 out of the 5 that are taken, right? How many positions are left for 2? 4. How many positions are left for 3? 3. How many positions are left for 4? 2. And how many positions are left for 1? For 5? 1. And this is called 14 choose 5, and it gives us 2002. But wait, the answer was 2001. Why are we getting 1 more? But well, here's the thing. This is a sequence that our algorithm here counts. But if we notice, it has all of the bars in front. So P immediately becomes 0. And then it prints out 0 5 times. So it's 0, 0, 0, 0, 0, which is just the same as writing 0. But the problem asks us 5-digit positive integers. Well, this is just a 1-digit integer. So we have to subtract this edge case. 2002 minus 1 equals 2001, our wanted answer.